INAF. He got his degree in 1997 about gravitational waves. And then he published from the University of Rome and just University in Baltimore, US, working about the formation. For subject thesis, and he is a staff astronomer at the Astronomical Observatory in Rome since 1993. He has been invited scientist at the European Southern Observatory ESO and also in the Astronomical Observatory of Paris. So guys, you are really going to enjoy the time we're gonna spend today with this afternoon with Dr. Nicola Menci. So Nicola, I'll give you a talk.
Okay. I'm trying to share the screen.
Okay, it should work now.
Yes. Okay. Do you see it? Can you hear me?
Yeah, we can. Yeah, we can see the screen, and yeah, we can hear you.
Okay, perfect. So let's move on. I would like to thank the organizers for having invited me to give this talk. The topic is quite big, it's quite large. So this is an overview of what I'm going to talk about. Since the topic is so large, and I will just give an overview of galaxy formation, please feel free to stop me and to ask me if you want to discuss in a closer detail one of the topics I'm going to discuss in this talk. So I would like to divide this talk in two parts. In the first part, I would like to discuss what are the properties of galaxies, morphologies, gas content, star formations, interactions, several properties that we know galaxies have in the local universe at present time. And the second part, I would like to actually discuss what is the big picture that is emerging from recent studies, observational studies and theoretical studies. What is the big picture that is emerging for the origin of these properties in galaxies? Okay. Especially, I would like to discuss what is the origin of these properties in a cosmological context. So within the evolving universe, what are the mechanisms that drive the formation of galaxies and determine their properties? Okay, let's start with the very, very close universe, our own galaxy. We know that actually our solar system is a part of a huge system, which is our galaxy, the Milky Way. The extension, the dimension of this system is incredibly large compared to the dimension of our solar system. In units of light years, you know, a light year is almost 10,000 billion kilometers. In terms of light years, our solar system is a fraction of 1,000th of a light year. And the extension of the Milky Way is something like 100,000 light years. So it's a system which is much, much larger than the whole solar system. And stars and gas are distributed mainly in a disk structure, which also shows the emergence of spiral arms. And surrounding this spiral structure, there is a halo, and at the very center of our galaxy, there is a third region called bulge. So the solar system actually is placed in a distant region of our galaxy compared to the central regions, and the typical distance from our solar system to the galaxy center is about 3.5 kiloparsecs. And the one parsec, I remind you, one parsec is something like 3.1 light years. And the rotation velocity of the sun and of the solar system around the center of our galaxy is something like 200 kilometers per second. So this is a very typical rotational velocity for spiral galaxies. And this means, given the dimension of a galaxy, this means that the typical period of rotation of stars around a spiral galaxy is of the order of 10 to the 8 years. So this is a typical time scale for rotation of stars and gas around the galaxy centers. And this also is a typical time scale for evolutionary features of galaxies. Galaxies change in periods which are longer than 10 to the 8 years, okay, over hundreds of millions years. These, of course, I just show you some artist view of our galaxy, because we are inside our galaxy and we cannot take a picture of it from an external point of view. But we can have we can take a picture of it from inside, and actually this is a very nice picture which is taken from Cerro Paranal in Chile, where the VLT telescope is placed, and the big strip that you can see in the sky is the Milky Way, is our own galaxy as seen from inside. Since we are inside the disk, you see is a strip in the sky, and you also see that there are these nebulous regions around, and these are the Magellan clouds. They were, of course, observed by Magellan, who, of course, could not have an idea what they were, but they are indeed galaxies which are satellites of our own Milky Way. They are small galaxies which are orbiting around the Milky Way. So we are discovering that galaxies have also satellites orbiting around them. Indeed, our own galaxy has several satellites. This is just a sketch of some of them. There are tens of satellites of the Milky Way. The small and large Magellan clouds are just two of them, but there are at least 30 satellites around the Milky Way. In addition, the Milky Way is not isolated from other big galaxies. It is indeed, it is part of a larger system which is called the local group. And there are two other big galaxies like the Milky Way, similar to the Milky Way, yes, which are part of this local group. These are Andromeda Galaxy and the Triangulum Galaxy. And these three galaxies are the main galaxies in a large structure which is called the local group. You see the dimension of the local group is shown in the sketch. You see that there is a bar showing the dimension of 1 million light years. So it's several million light years. And this structure, the local group, is a bound structure which contains tens of galaxies. So we see that galaxies are not uniformly distributed in space, but they are clustered. There are satellites orbiting around the larger galaxies, and in turn, large galaxies are clustered and they group into larger structures. So this is a picture of a galaxy which is similar to our own galaxy. This is the Andromeda Galaxy. And this was the first object that was discovered to be a galaxy outside our own galaxy. Indeed, in 1923, Hubble discovered that Spiral Nebula were actually galaxies outside our own galaxy. And this instantaneously expanded the dimension of the universe by a huge factor, because the universe, there were a lot of these nebulous objects, which now became clear that were actually external galaxies. So one property, one very important property of spiral galaxies, like the Andromeda Galaxy and our own galaxy, is that they are gas-rich, and they are forming stars at rates which can range between 1 to 100 solar masses per year. So this, how do we know that they are forming stars? Because there is a lot of blue light emitted from the disk, and since the UV and blue light is emitted mainly by OB stars, and since the lifetime of OB stars is small compared to the typical timescales of a galaxy, we know that all these stars have been formed recently, and this blue light is emitted by stars that formed recently. So we know that there is ongoing star formation. And in addition, we know that there is a lot of gas, of course, and it is possible to correlate this rate of star formation with the gas content of the galaxies. And this is done in these plots. It's actually an observational. There is an observational correlation between the density of star formation, the surface density of star formation that you can see in the y-axis in the plot here that I show in this slide, as a function of the density of gas in the disk. And as you can see, the larger is the gas density in the disk, the larger is the star formation rate of spiral galaxies. So they range from, let's say, a few solar masses, a fraction of solar masses per year to hundreds of solar masses per year in terms of star formation rates. This law relating the intensity of star formation to the density of the gas is an empirical law, but it can be actually understood if one considers that star formation is a gradual process which gradually converts part of the gas in the disk into stars. And the typical timescale for actually converting this gas into stars is of the order of a gigayear. So spiral galaxies are continuously converting gas, which is cold in the sense that is at a temperature of about 10 to the 4 kelvins, is converting this gas into stars at a in a continuous process, which is called quiescent star formation, with a time scale which is of the order of a gigayear. Okay. So associated with this continuous star formation, there is also expulsion of gas from spiral galaxies. This is a very important process which is called supernova feedback, and it's related to the fact that supernovae following star formation explode in quite a short time scale, millions of years, and this expelled and heated gas actually yields strong outflows from the galaxy, which can be seen in X-rays. In the image, you see a combination of X-rays and optical image to show the outflow of this gas expelled by supernova events from a galaxy which is intensely forming stars. This gas is heated by supernova at temperatures of around 10 to the 5 to 6 Kelvin degrees and is expelled from the galaxy. The UV and blue light, the efficiency mainly of gas expulsion by supernovae depends on the mass of the galaxy. Okay, if the galaxy is a big galaxy, a galaxy with a very strong gravitational potential, as you can see in the right in this animation, this movie, then the expulsion is not very efficient because the potential wells, the gravity of the galaxy is so strong that keeps the gas close to the disk. If, however, the gas is in a small galaxy, like you can see in the left of this slide, with a small mass, then the gravity of the galaxy is not strong enough to keep the gas confined into the disk or into the galaxy, and the gas is efficiently expelled out of the potential wells. So there is a continuous process of gas expulsion following star formation in spiral galaxies. So spiral galaxies, of course, are not the only kind of galaxies that you can find in the sky. Elliptical galaxies are a completely different population of galaxies. They have different properties, and the main properties is that they actually include evolved stellar populations. The stars in elliptical galaxies are old, more than 8 gigayears old, usually, and the elliptical galaxies are gas poor and they have very low star formations. In addition, their kinematics is dominated by random motion of stars, and this is another difference from spiral galaxies, which is important to underline. what you can see is that in general, gravitational systems and galaxies in particular can actually stay in equilibrium because of two different processes. Okay, in spiral galaxies, as you can see in the lower left corner of this slide, in spiral galaxies, the motions are typical rotations. It is an ordered motion around the center of a galaxy in the same direction. Okay, the centrifugal force balances the gravity, and this keeps the system in equilibrium. On the other hand, in elliptical galaxies, stars have random motions. They do not have a specific directions of motion. This random motion provides a pressure term which balances gravity. So there are two different ways of staying in equilibrium with the gravitational potential. Elliptical galaxies, spiral galaxies, and irregular galaxies, which is another kind of galaxies, occupy different positions in the mass distribution of galaxies. Okay, in particular, elliptical galaxies tend to be massive galaxies, while spiral galaxies dominate the intermediate mass range of the mass distribution of galaxies. This is a more quantitative plot that tells you essentially the same thing. You can see that the purple curve, which corresponds to the elliptical, to the spiral galaxies, is peaked at intermediate mass. So in terms of stellar content for galaxies, it's something like 10 to the 10.5 or 11 solar masses, while elliptical galaxies, the distribution of elliptical galaxies stretches toward very large masses. So elliptical galaxies dominate the massive end of the mass distribution of galaxies. There is another very interesting population of galaxies, and this is constituted by interacting galaxies. This is a beautiful picture taken by Hubble Space Telescope showing two spiral galaxies interacting. And this is quite a common process. Of course, in the local universe, something like 10% of galaxies are in interaction. Okay, this is a gallery of these interacting galaxies, and they have an interesting property that I'm going to show you in detail in the next slide. The first one, of course, is this kind of disturbed morphology, that the interactions tend to cause the formation of tidal arms, as you can see in the simulations in the left, and as you can see also in the observation of this Andromeda Galaxy on the right. So this disturbed morphology is a sign of a galaxy interaction. The second very important property of interacting galaxies is that they actually form stars at a very, very high rates. They can form stars at rates which can go to values as close to 1,000 solar masses per year. So there's a huge amount of star formation, as you can see also in these blue spots, which characterize these images of interacting galaxies. Okay, so this very intense star formation is an additional channel for star formation, and it's a channel which is different from the quiescent conversion of stars that we have seen in normal spiral galaxies. Okay. So if you actually look at the distribution of star formation rate as a function of the gas mass, you can see that the quiescent star formation gives you star formation rates which are of the order of tens solar masses per year, and starburst interacting galaxies give you much larger values. There's a final thing about the properties of galaxies, and this is the existence of a dark component, which is called dark matter. This means that there is a dominant, a dominant component of galaxies, which is in a form which is not visible at any wavelength. It's not visible in the optical, in the infrared, ultraviolet. We can infer the existence of this matter from the velocity that actually produces on test particles. So just to give you an example of how we know the existence of dark matter, let's give a look. Have a look at the solar system. Okay, in the solar system, 90% of the mass is in the sun, is in the center of the solar system, and the velocities, the rotational velocities of the planets, have to balance the gravity of the sun. Essentially, to balance the gravity which is produced in the center. Okay, so the balance between the velocity, the centrifugal force, and the gravitation is shown on the top. And this means that as you go to larger and larger distances from the center, the gravity gets weaker, and you have smaller, lower rotational velocities, because you have you have a weaker gravitational force, and then lower velocity are necessary to balance this weaker gravity. So if you do the same experiment in a spiral galaxy, you can see that most of the light is emitted in a central region. Then you want to explore what happens at very large distances from the center, and you can use as test particles the particle of a neutral gas which is orbiting around galaxy. And if you use these test particles orbiting very, very far from the galaxy center, where all the gravity is supposed to be, if you measure these rotational velocities, you find that these rotational velocities are not as small as you would expect if all the mass was concentrated in the center. These rotational velocities are much larger than what you would expect if the visible galaxies is what contains most of the mass. This means that there is a huge amount of mass extending from the central region to the distant regions where we are actually looking at the rotation. This very large mass, which is responsible for such large rotational velocities, is called dark matter. This is a sketch. This is an animation shows you on the left what would happen if all the mass was indeed in the visible galaxy. And you can see that in peripheral regions, there are very slow rotational velocities. On the right hand, you have what happens in the case of dark matter distributed between the center and the outer regions. So you see the rotational velocities are large. Since we actually measure large rotational velocities, this means that there is a large content of dark matter, which can actually be as much as 90% of total mass of the galaxy. Okay, so we have seen different properties of galaxies. We have seen the galaxies tend to cluster, to be placed in structures which can be groups of galaxies, like the local group. But galaxies can also stay inside larger structures, like galaxy clusters. These are regions which have a dimension of something like a few megaparsecs, that is a million, tens of millions of light years. And this is a beautiful image of a galaxy cluster. The typical velocities of galaxies inside the galaxy cluster is something like 1,000 kilometers per second. And in the central regions of galaxy clusters, usually you find a giant elliptical galaxy, which is, as usual, a gas-poor galaxy with a very low star formation rate. And there's another evidence of dark matter from galaxy clusters, because you can actually measure the motion of galaxies inside a galaxy cluster. The motion of galaxies inside a cluster is something which is similar to the motion of stars inside an elliptical galaxy. It's a random motion, and this results into a pressure term which balances gravity. So in galaxy clusters, gravity is balanced by the random motions of galaxies. But since you can measure the average velocities of this galaxy, you can also measure the depth of the potential wells, and you can measure the mass of the galaxy cluster. And this mass turns out to be something like 10 to the 15 solar masses, so a million billion times larger than the mass of the sun. And this is a value which is much larger than the sum of the masses of the galaxies which are included in the galaxy clusters. So this is a strong indication for the existence of dark matter in the cluster volume. This very large dark matter content is actually responsible for the large speeds, the large velocities that we observe in the random motion of galaxies inside the cluster. There is another evidence for this. It is given by the temperature of the hot gas, which is actually filling the galaxy clusters. Galaxy clusters are filled with hot plasma with temperatures of about a million, something less than a billion degrees. And this very large temperature indicates that the gas particles are moving with very high speeds, very high velocities, and these very high velocities, which are actually are observable in terms of temperature of the gas, are again an indicator of the large masses that you find in galaxy clusters. Okay, so the temperature of the gas is a measure of the random motion of gas particles, and this must balance the gravitational potential. This means that the gas temperature is a measure of the mass of a galaxy cluster. And again, if we perform this measurement, we measure a mass of the galaxy cluster, which is about 10 to the 15 solar masses. So it's a very, very large mass. So this means that actually, if we look at the density field in a galaxy cluster, like it is done in this simulation, we must think about galaxies as the tip of the iceberg. Okay, so what you see in the big image is the distribution of dark matter. White colors indicate large densities of dark matter. So there is dark matter inside, filling the galaxy cluster, and there are condensations of dark matter inside the cluster. Each condensation of dark matter is the halo of a galaxy, and the visible part of the galaxy is located at the center of each one of these clumps. Okay, so the visible galaxies are the tip of the iceberg of a much larger distribution of dark matter, which extends over the whole cluster volume. Okay, so we can actually summarize what we have just said using this animation, which shows you a virtual trip to the Virgo cluster starting from our galaxy. It's a trip which starts inside our own galaxy, and this, we are now traveling in the direction of the Orion Nebula. And as you can see, this is a region of star formation, which is actually a region of star formation inside our own galaxy. This is the Horsehead Nebula. And you can see other regions of star formation, or you can see open clusters of stars. You can see also in this animation, you can see the supernova in the Crab, which has been discovered more than 1,000 years ago. And you can see also, of course, billions of stars floating around in the disk of our galaxy, and a huge amount of gas which is filling the disk of our galaxy. So as the animation now moves from the plane of the disk, you can appreciate the huge dimension of our galaxy, and you can appreciate the disk structure of the regions where most of the stars and gas are placed. And as the animation moves out from our galaxy, you can also see small Magellanic Clouds on the left, which are satellites of our own galaxy. And you can see also that in the background, there are thousands and thousands of other galaxies which are placed not in a uniform distribution, but they are concentrated in some regions. The two galaxies that you are seeing now are the Triangulum Galaxy and the Andromeda Galaxy, which are the two main galaxies in our local group. So we are now starting to leave our local group, and we are heading to the Virgo cluster. And as you can see, outside the high density regions, in regions where the density of galaxies is smaller, you have a lot of spiral galaxies. Almost all galaxies that you can meet outside the high density regions are spiral galaxies. However, as we go toward the Virgo cluster, and as we approach high density regions, you can see that the fraction of spiral galaxies decreases, and the elliptical galaxies start to dominate the distribution of galaxies. In other words, elliptical galaxies tend to stay in dense environments, while spiral galaxies tend to stay and to live in lower density environments. This is another very important properties of galaxies that we want to explain in our galaxy formation scenario. This is the center of the Virgo cluster. This is M87, mostly the big galaxy at the center of the Virgo cluster. And of course, it is an elliptical galaxy with a huge black hole at the center. So this is a plot which shows you quantitatively that elliptical galaxies are found preferentially in dense environment, while spiral galaxies are found preferentially in lower density environments, outside galaxy clusters and in low density regions. Okay. If we want to go further out, we want to see how galaxies are distributed at even larger distances, then you can actually look at surveys of galaxies, which are collections of thousands and thousands of galaxies, a collection of positions of galaxies in the sky. And they started to be actually, this kind of study has been started in the 80s. And since then, we know that galaxies are not uniformly distributed even at larger distances. They are actually distributed along filamentary structures, which are called large-scale structures of the universe. So there are void regions, and there are regions, filamentary regions, where most of galaxies are concentrated. This very dishomogeneous feature of the universe is something which, of course, requires an explanation, and it's actually the final structure of the universe on scales of about 100 megaparsecs. On larger scales, the universe seems to be uniform in the sense that these structures repeat, but there are not even larger structures. This is another representation of this very dishomogeneous distribution of galaxies in the sky. You can see the Virgo cluster, where our travel ended, and around it you can see these filamentary structures standing for hundreds of megaparsecs, so huge distances. Now, what we would like to do now is to understand the origin of all these properties. Okay, what is of the origin of galaxies in a cosmological context, in the context of the Big Bang evolution, of the evolution of the universe starting from the Big Bang. We would like to understand if galaxies have been evolving over cosmic times. We would like to know why galaxy masses span such a large range of masses, why galaxies are clustered and distributed along large-scale structures, why they try to concentrate sometimes in galaxy clusters. And we'd like to know what is the origin of this of different morphologies, what is the origin of their different star formation histories, why elliptical galaxies, for example, have such low star formation rates, why they are gas poor, why the kinematics of ellipticals is so different from spiral galaxies. And we would like to also understand why massive ellipticals are found preferentially in dense environments, and so on. We'd like to actually investigate the origin of all these properties. So I would like to give you now a picture that is emerging from recent advances in observations and in theory. Of course, this picture is not the final picture we are building up at the moment, but it is a reasonable picture which we are testing more and more with new observations, which will be even better tested in the near future with upcoming facilities like James Webb Space Telescope or the Extremely Large Telescope of ESO. So let's start from to investigate the cosmological origin of galaxies. To understand it, let's try to summarize what we know about the expansion of the universe. Of course, as you know, since the discoveries of Hubble in the 20s of the last century, we know that galaxies are moving away from each other at velocity which is proportional to the distance. And this indicates the whole universe is expanding. So the space between galaxies is stretching, and this stretch results into this motion, which is moving, which constitutes the Hubble flow. Okay, so galaxies on average are moving away from each other. Of course, this is only average motion. Okay, locally, galaxies can also encounter, as we have seen in the first slides. But as in the average, when you make averages over very large volumes, then the average motion is a motion in which galaxies are moving away from each other because of the stretching of space-time. So if we actually go back in time, then we have to consider the universe in the past epochs was much denser, much hotter. And this means that after the Big Bang, the universe cooled, and as it was cooling, the primordial particles that compose the primordial soup of particles in the universe start to give rise to the matter that we know today. For example, when the universe was very young, 10 to the minus 12 seconds, these particles started forming the nuclei and protons, the nuclei, the protons, and the nucleons, and then this nucleons started to form the nuclei of the elements that we know today. But until about 300,000 years after the Big Bang, the nuclei and the electrons were not did not give rise to atoms. The temperature was too high for electrons to recombine with the nuclei to give rise to atoms. When the temperature dropped below something like 3,000 kelvins, then the electrons started to recombine with the nuclei to form atoms. At that point, the photons, the radiation that was continuously scattered by free electrons, was propagated through the universe. And this radiation is still coming toward us today. It is an echo of the Big Bang. Of course, the universe has expanded and cooled since that time. So the temperature of that radiation, which was something like 3,000 kelvins at that time, now it is much lower. Now it is only 3 kelvins, because the universe has expanded and cooled, and this radiation has also been stretched to longer wavelengths, and the temperature is low. But this radiation is still around today, and it's what remains. It is the relic of this early stage of the universe. So this radiation is called cosmic microwave background, and it is the radiation which was emitted when the universe was about 300,000 years old. And this radiation was predicted already in the 50s of the last century to be a black body radiation, okay? And this black body radiation was indeed observed in the 60s of the last century by Penzias and Winslow, which were two engineers which were trying to actually set up the antenna of a radio device that were trying to operate. And they noticed that this kind of noise didn't disappear, and predicted already in the actually it couldn't disappear because to be a black body origin. It was the relic of this early phase of the universe. Now the point is that this macro background is not completely uniform. Okay, this is a very important discovery of the 90s century. which led to the Nobel Prize for Smooth Matter. And as you can see in the upper right part of this slide, this microwave background radiation is not completely uniformly distributed in the sky. What you see is a picture of this of the temperature of this microwave background. This means that blue regions are lower than temperature regions, and red regions are higher temperature regions. These fluctuations in the temperature of the microwave background are very, very tiny. 1 part over 100,000. So there are very, very tiny fluctuations, which are exaggerated in the picture. However, nevertheless, they exist, and they actually indicate that the plasma, that the matter filling the universe at that time, was not completely uniform, but it was characterized by small density fluctuations, which were as small as 1 part over 10 over 100,000, but nevertheless was not homogeneous. And these small dishomogeneities in the very early phase of the universe are the seeds from which all the cosmic structures that we observe today are formed. Okay. So to see this in detail, let's consider some very important properties of these density fluctuations in the early universe. So you can actually investigate whether fluctuation on different angular scales have the same or have different amplitudes. Okay, what I mean is, as you can see, for example, in this image of the seawater, you see that you have larger waves and also you have smaller waves. So the same thing, same situation occurs in the cosmic microwave background. You have small scale fluctuations at the bottom, and you have also larger scale fluctuations. Okay, so if you analyze what is the amplitude of fluctuations involving different angular scales, what it turns out is that on average, large scale perturbations have smaller amplitude compared to small scale fluctuations. So in this sketch, I show a portion of this initial density field, and you can see the fluctuations. There are the orange fluctuation, which involves a large region of the initial density field. There is the green fluctuation, which involves a smaller region of the density field. And on average, small-scale fluctuations have larger amplitudes compared to large-scale fluctuations. Okay, this is a very important property that is emerging from the observation of the microwave background. And so what we can do now is to actually reproduce this kind of fluctuations in the primordial distribution of matter in the universe. So we reproduce on a computer the density distribution of matter in the universe with tiny fluctuations which have the same power spectrum. And then we let evolve this distribution of matter to see what happens. And this is done in the next picture. Of course, what you expect is that dense regions become denser and denser, and under-dense regions will become void regions. Okay, but we'll see this in this simulation where we start from very high redshifts, from very early times, with tiny matter fluctuations, which correspond to the tiny fluctuation in the cosmic background. As you can see, from these very tiny fluctuations, gravity causes small-scale fluctuations to collapse to form the first galaxies. And these are the lighter dots in these simulations. And these small-scale fluctuations grow with time and merge sometimes and build up larger and larger objects. And this, as you can see, from these very tiny fluctuations in the cosmic, the primordial density field, you are able to reproduce the filamentary property of the galaxy distributions today. There are huge filaments of matter extended from on megaparsec scales, and at the knots formed by the intersection of these filaments, you will see that galaxy clusters will form, like the one that is forming at the center of this simulation. Okay, and the blobs corresponding to the galactic halos are getting larger and larger because of the merging of these initially small clumps collapsed from the primordial density field. So this is what we think is at the origin of galaxy formation. Of course, we can have a closer look at this process by studying a particular region in the density field. If we enlarge, for example, this region, and we actually simulate what happens in such a region, you will see that the first clump that form from the collapse of initial density field are small mass clumps. They merge together to form larger and larger structures. You will have strong and intense interactions at early times. These are major interactions, as you can see. After some time, let's say after a few giga years, the interaction rate decreases a lot. Merging events are rarer and rarer, and a spiral galaxy is forming, and this gradually accreting matter and becomes a spiral galaxy as the ones that we see today. So the origin of the rotation for this galaxy is given by the surrounding galaxies, which are continuously interacting, and the torque arising from this non-uniform distribution of matter around the proto-galaxy determines the rotation of the spiral galaxy. Okay. Of course, gas is falling into these forming structures. For example, in the top right panel, you see the gas temperature. You see that while structures are forming, there is hot gas filling the large volumes that will give origin to a galaxy cluster, and this will be the origin of the hot gas that you find in galaxy clusters. On small scales, on the other hand, the gas density, the gas temperature is much lower, and this gas will be funneled to the center of spiral galaxies, will lead to the formation of stars that we observe today in spiral galaxies. Now, so we think small mass clumps. We have this picture for galaxy formation from very tiny initial perturbation of matter. We think that the large-scale structures and the galaxies have formed through gravitational instability. Okay, it's a kind of amplification process. The amplification is due to gravitational instability. It's mathematically similar to the amplification of the small light fluctuations on the surface of a swimming pool. The surface, the small wiggles in the surface of a swimming pool act as amplifiers of the light rays that are coming, and at the bottom of the swimming pool you will see a network of light that is indeed very close to the network corresponding to larger scale structures, because it's a kind of similar process. It's the amplification of a tiny density or tiny perturbations by some process. Okay, in the case of galaxies, this process is gravitational instability. So now we want to test this picture. Of course, we have a picture for galaxy formation. It is an interesting picture, but we'd like to know if this corresponds to real observations. To know that, we should do is to go to distant universe and to observe early galaxies to see that to see whether these early galaxies are still in the act of merging, of interacting, of building up those large galaxies that you observe today. Now, since the 90s, in the last century, this was a very difficult task, but with the advent of powerful instrumentations, like, for example, the Space Telescope, it became possible to actually look at very, very distant galaxies. And since, of course, the light travels at some finite speed, then if we observe very distant galaxies, we are observing galaxies which, as they were many, many years ago. So it's a kind of time machine. We can see galaxies as they were many years ago if we observe distant galaxies. Now, this is an image of a barred spiral galaxy. And I would just like to draw your attention on the difference between what we had before the advent of instruments like the Hubble Space Telescope and the image that we had later on. You can see that we can have beautiful details of the close galaxies, but we also are in the condition of having images of very, very distant galaxies in the background. So we are now in the position of investigating the very first object in the universe. And the very famous program aimed at this was the Hubble Deep Field. It aimed at observing an empty space, an empty region of space close to the Ursa Major, and this was chosen to be free from local galaxies, from galaxies close to us. And they let the space telescope observe this apparently empty region for days and days. And at the end, the integrated image led to this beautiful picture where in this apparently empty region of sky showed that thousands of galaxies, sometimes very, very distant from us. The most red objects are the most distant galaxies because their light has been stretched toward red by the universe expansion. And this beautiful image is known as the Hubble Deep Field. So if we now have a look to the most distant galaxies, to the most red objects that we have in this picture, we see that they are very different from our galaxies. This in this slide, I'm showing you the most distant galaxy detected until now. It's a very, very distant galaxy at a redshift 10, something or 11, which corresponds to something like 450 million years after the Big Bang. So we are in the condition of looking at very, very distant objects. Okay. So if you look at these very distant objects, what we can see is that they don't look like the galaxies that you observe today, and they don't have the nice elliptical or spiral shapes, but they have indeed very disturbed morphology. Okay, this is just a snapshot of a few of these objects taken from the Hubble Deep Field. Most of them are irregular and merging objects. They show signs of interactions with other galaxies. This is a gallery of these objects. Almost all of them show sign of interactions, and also they are very much smaller than the local galaxies. Okay, so this is a comparison of present-day galaxy on the top left to the very distant galaxies in the bottom right, and you can see that galaxies have evolved a lot during cosmic time. Okay, starting from very small, irregular, disturbed morphologies to the regular morphology that we observe today. So this is another collection of interacting objects. And as I told you, those objects are typically much smaller than our galaxy. And finding so many of these small mass objects is a strong indication that the galaxies built up through a gradual process of growth and interactions and merging. And another important point is that these galaxies are very blue. You can see them red because of the light, because the light has been stretched by the expansion of the universe. But the intrinsic emission is indeed very blue. This is a strong indication, as I told you, of an intense star formation. So these galaxies are actively forming stars at very high rates. They are interacting galaxies. Most of them are merging galaxies, and they are probably the building blocks of galaxies that we saw today. And this is a strong indication that the picture that I gave you is quite correct. So there's another way of observing distant galaxies, and this is thanks to the gravitational lensing. For example, what you see here is the effect of a galaxy cluster. So the light of a background galaxies is bent and amplified by a galaxy cluster which is in the foreground. So we can use galaxy clusters as telescope to reconstruct the light of background galaxies and sometimes of very distant galaxies. This has been done, for example, in this case. What you see is an image of a galaxy cluster, but some of the points in this image, the one enlightened by circles, actually correspond to background galaxies whose light has been amplified by gravitational potential of the cluster. This is another way of looking at distant galaxies, and again, galaxies that we discover in this case are again irregular galaxies with disturbed morphologies and with very intense star formation. Okay, so primary galaxies are very different from local ones. They have these irregular morphologies, interactions, intense star formation. There are a huge number of these irregular galaxies, so there is a strong indication that the galaxies that we see today have been assembled from smaller building blocks. So this is actually one of these processes of galaxy assembly, which has been caught in the act. It is the so-called spiderweb galaxy, where it's a galaxy at redshift 2.2. This means that it's been this galaxy is forming something like 10.6 billion years after the Big Bang. And what you see here is the assembly of a massive galaxy through many small mass clumps, which are actually accreting and merging with the main progenitor to form what will become today a massive galaxy. So we are now starting to see this process in the act. So what is the origin of different morphology between of spiral galaxies and elliptical galaxies? Why they are so different? So one explanation, which is consistent with the picture that I showed you before, is that for the spiral galaxies form in regions of the primordial density field which are not so densely populated. Okay, elliptical galaxies form in overdense regions. So they form very early because there are a lot of small mass clumps which are rapidly merging to form massive objects. And this rapid accretion of objects, which provides a very strong star formation rate initially, but also destroys every disky distribution of stars. On the other hand, spiral galaxies form in lower density environments. The assembly is much more gradual, and the accretion of small lumps is not able to destroy the disk structures. Okay, so that's how we actually think about a possible origin of the difference between the elliptical galaxies and spiral galaxies. So the difference actually can be traced back to their different history, assembly history. This is a merger tree. It's the diagram which actually tells you how a galaxy that we see today at redshift 0 is assembled from smaller pieces at very high redshifts. Okay. So if we look at the average star formation history of the universe, this is actually has a very peculiar shape. It's characterized by a very rapid increase at very early times, high redshift. That means look-back times larger than 10 gigayears, and by a decrease at very low redshift. This means that at very early times, there is a phase of rapid assembly of galaxies. There are frequent interactions. These frequent interactions triggered very intense and active star formation, and the curve started to grow. At redshift 2, corresponding to a time when the universe was 2 gigayears old, this process started to dwindle, and the interaction rate decreases, and this decrease of merging rate also was also produced a less intense star formation. In addition, the gas gradually is converted into stars, because we know that gas in spiral galaxies, for example, is gradually converted into stars. So there is a progressive exhaustion of gas reservoirs, and this means that the star formation rate decreases. So the average star formation history of galaxies in the universe is characterized by an early phase with a rapid assembly of galaxies, rapid star formation, rapid growth of the gas content and of stellar content of galaxies, and by a maximum peak where the star formation rate was maximal at redshift 2, and by a later decrease of star formation due to the decrease in the merging rate and to the gaseous exhaustion in gas. Because this is the average star formation history of the universe. But if we see what happens in spiral galaxies and in elliptical galaxies, that's what we have. So in elliptical galaxies, this very early phase was particularly intense. So there was a very, very rapid assembly of clumps into a massive galaxy. And there was a very, very intense and active phase of star formation. This happened very, very early at a very high rates. But after this very rapid phase of galaxy assembly, the gas was completely burned out. It was completely converted into stars. And the subsequent evolution of this system was characterized by a passive evolution. The gas was completely exhausted, completely converted into stars. And from a few giga years after the Big Bang until now, those objects didn't form stars anymore. So they became the red, passive, gas-poor galaxies that we observe today. Conversely, spiral galaxies form in lower density environments. Their star formation and their assembly proceeded through a much more gradual process. Star formation was much more gradual. Their interaction rate was lower. So these objects were able to retain a major fraction of their gas for subsequent star formation. So these galaxies are still forming stars until today because they were able to retain part of their gas. They didn't exhaust, they didn't convert all their gas in stars at very high redshifts. They are much more extended star formation rate. Okay, this is another sketch to show you more or less the same thing. Okay, elliptical galaxies, spheroids are characterized by rapid star formation and rapid assembly at high redshifts. On the other hand, spiral galaxies formed much more gradually, much more extended. It's a process which has been much more extended in time. Okay, so this is what the final picture. In overdense region, there is a rapid gas inflow, star formation, rapid exhaustion of gold gas, expulsion of remaining gas due to supernova feedback. We know that this is a process which is common, and this leads to final objects which are elliptical gas, which are depleted of gas, and which are only including all stars that formed at very early in the cosmic history. In less dense regions, on the other hand, there is a much more gradual inflow and gas cooling. There's much more gradual star formation and less extreme feedback events. And all these things left a large fraction of gas available for subsequent star formation. So the final spiral galaxies are still forming stars. Okay, I think I would like to stop here because we actually covered many topics. And I would like to leave the remaining time for questions. If you have, I will be happy to answer to your questions. Thank you.
Thank you, Dr. Nicola, for the nice presentation. It was really very interesting to learn more about galaxy and galaxy formation. So we are welcoming now any question. So we're gonna start with the group here, and then we can go to check our live in the page. So does someone have a question? Okay, Dr. Nicola, from our side, we do have two questions. The first one is, how can we say that every galaxy is descending away from any other galaxy? How we can determine that?
It's just statistical measurements. We measure the velocity of a huge number of galaxies, and we make a plot where on the x-axis we show the distance of these galaxies, and on the y-axis we plot the velocity. Okay, and we see that on average, okay, this diagram is characterized by a linear correlation. This means that most distant galaxies are receding are going away from us at higher and higher velocities. But this is true only on average. Okay, so the point is that Hubble was really lucky because he actually derived this plot with a very limited number of galaxies. As you can see in this plot on the bottom right, this is the original Hubble diagram. Okay, and he discovered this law with just a bunch of galaxies. But if we actually enlarge the sample to a much larger number of galaxies and to much larger distances, we see that this plot is valid. It is valid only on average. Okay, there are dots in this diagram which will not obey to this law because there are local motions, of course. But if you make the average over a huge number of galaxies, this is the average relation that you find. Okay.
Mm-hmm. Another question that, how do you know that the stars form galaxies? What kind of like study or research that allow us to say, okay, these stars could make galaxy in the future?
No, I didn't understand the question, sorry.
How could we understand that group of stars could form a galaxy? What kind of study do we use to say, okay, this group of stars could form a galaxy?
Well, today we find stars essentially in galaxies. All stars that we know, almost all the stars that we know today are inside galaxies. Okay, so if you start from observations, they are belonging to a galaxy. Now the question is, how do we know that in the past they belonged to different galaxies? Okay, and that those different galaxies have merged to form the present galaxy. This is a different question, of course. And this, again, comes from the study of the properties of these stars. For example, in the Milky Way, there are different populations of stars. Okay, some of them are very old, some other stars are very young. For example, most of the old stars are in the bulge. And so we think that the bulge was formed early on in the history of our galaxy. Okay, but of course, all the stars that we observe today are in a galaxy. Okay, the point is that how we understand that they were part of different galaxies in the early phase of the universe. Okay, I don't know if I answered your questions.
I did. We do have another question from Zina. She say, we study the universe as the whole, so it is homogeneous and isotropic. Also, we say that there are some regions are more dense than another ones. Can you explain it more?
Well, explain the homogeneity of the universe at large scales. That is the question.
Yes, she say that the universe is whole, as like something homogeneous and dense. There are some part of the universe is more like dense than another region. Why? For which reason?
Okay, so we think that these differences among different regions in the universe are only on relatively small scales. Okay, so if you see, for example, this plot here, okay, this image here, this shows you the large-scale structure of the universe. In this case, the universe is very, very inhomogeneous because we are looking at scales of about 100 megaparsecs, okay? And at such small scales, the universe is indeed very dishomogeneous. There are empty regions and filaments and so on. The point is that when we observe the universe at much larger regions, at much larger scales, this seems to be indeed much more uniform. Let me try to find a slide to show you some detail. Just a minute. You can see this is a simulation over 1 gigayears, okay? The dimension now is much larger. So you see that it is inhomogeneous only when you look in a sufficiently high detail. When you look at regions smaller than hundreds of megaparsecs, you will see that the universe is composed, as a structure of voids and filaments. But when you look at very, very large distances like this one, okay, the universe seems to be homogeneous. So on scales larger than, let's say, hundreds of megaparsecs, then the universe as a whole seems to be homogeneous. When you collect a huge number of galaxies in these galaxy surveys, and you track the position of each galaxy in the sky, and you reconstruct the galaxy distribution, the picture is that on small scales it is granular, but when you go to very, very large scales, then it's every direction is equivalent. So from the galaxy surveys that we actually have performed until now, we know that this seems to be the situation. The universe is homogeneous only on scales smaller than, let's say, 300 megaparsecs.
Okay, we do have another question, Dr. Nicola. What is the most popular theory about what could be the center of galaxy?
The bulge of the galaxy, you mean?
Yeah, the center of our galaxy is like necessary is a black hole, or what is the most accepted theory about the possible material of the center of each galaxy?
Okay, so if you're talking about black holes, supermassive black holes at the center of galaxies, so it's in the bulge of we think that in each bulge of each galaxy there is a supermassive black hole. Okay, observations seem to indicate that in the bulge of each of galaxies there is a supermassive black hole. What is the origin of these black holes? This is very much debated, the issue, because there are two possibilities at least. One possibility is that the first generation of stars in the very early galaxies, the primordial galaxies that we were talking about, the very early population of stars is called POP3 stars. They were very massive stars that produced very massive black holes. So the original black holes inside the proto-galaxies were produced by the collapse of very massive stars. Okay, these primordial black holes, so these black holes formed in primordial galaxies, would be as massive as 100 solar masses, something like this. Okay, in the subsequent phase of galaxy evolution, these primordial galaxies merged to form larger and larger galaxies, and during this process, a very large gas mass was destabilized from circular motion. It was funneled toward the center, and this increased the black hole mass from the initial 100 solar mass to 10 to the 8, 10 to the 9 solar mass that we observe today. So it was a process, a gradual process of a black hole assembly, black hole growth, starting from 100 solar masses black hole produced by very early stars in very early galaxies, which continuously accreted material from the growing galaxies. Okay, the problem with this scenario is that we observe very massive black holes early on in the history of the universe. So we observe black holes as massive as 10 to the 9 solar masses, as a billion solar masses, as early as redshift 7 in the history of the universe. So it's very, very difficult to make those initial black holes grow fast enough to build such massive black holes at those redshifts. So this is a problem with this scenario. The other scenario is that in early galaxies, in the primordial galaxies, there was the rapid collapse of a huge gas clamp of 10 to the 5 solar masses. In this case, this initial black hole was not formed by stars, but it was formed from the collapse of a very large gas mass. In this scenario, it's much easier to, of course, to accrete gas so as to produce massive black hole early on in the history of the universe. So this problem is less severe. But on the other hand, there is the other problem that is not easy to imagine how such a large gas mass can collapse to form a central black hole in a rapid time without fragmenting. So both scenarios that have been proposed so far have some advantages and some problems, and we still don't know what is the right scenario. What is certain is that the black holes that we have today are formed from primordial seeds, which could be massive or less massive, and that all these seeds have growth through gas accretion. But we don't know the origin of initial seeds. Okay.
Okay, we do have another question from one of participants. It say, what is inside the black hole?
We think that there is just space, very curved space, and that's all. To presume that there is just curved space, we don't know what we find inside the singularity, which is the point where, of course, general relativity breaks down without without the help of quantum gravity. But inside the event surface, we think there is just a curved space. That's all. I know that this is not a very satisfactory explanation, but that's what we know.
Okay, another question is, how did scientists take picture of our galaxy? Because they are now a spacecraft to cap the shape of the galaxy.
We don't have images of our own galaxy from an external point of view, okay? As I showed you in this picture, of course we can have a picture of our galaxy from inside, and this is, you can have it without having a telescope. You just go to a place where you have a clear view of the sky, and that's the white strip in the sky is the disk of our galaxy. But of course, we don't have an image of our galaxy taken from outside the galaxy, because it is not possible to launch anything outside our galaxy. And in addition, it would take too much time to reach the point where you can take a picture of it. So we have pictures of external galaxies, and we have picture of our own galaxies, but taken from inside, okay? From inside the disk.
So what does that mean is, like, every picture that we have it from the desert or from Atacama or from Chile, for example, all of this is picture inside our galaxy. It's not the outside. It's like the border limit of our galaxy, just all. But we are sitting inside our galaxy.
We are sitting inside our galaxy, of course. Any telescope in the Earth or in orbit can only take a picture of our galaxy from inside. There is no way to take a picture of our galaxy from outside. Okay, we can take picture of other galaxies, of course, but not. We cannot have a picture of our galaxy.
Another question from Zina. She say, imagine if we replace dark matter by baryonic matter, the galaxy would be the same as now or not?
No.
She said, here we speak exactly about the properties of both of them, especially when we say that the gravitational field, how it would be.
Of course, no, it would not be the same. One of the effects of dark matter is to stabilize the disks, for example. So it would be very difficult to have a stable disk for spiral galaxies without dark matter. Okay. The other point is that probably we would not have galaxies forming in such a rapid lapse of time if dark matter was not present. Let me say, for example, if you look at this picture here, okay. So we know that when the universe was only 300,000 years old, the matter in the universe was a hot plasma. We didn't have galaxies at all. Okay, so we must have formed galaxies in a rather short amount of time, because we know that the galaxies were already in place 500 million years after the Big Bang. So in a short amount of time, galaxies were formed. So if we only had baryons in the universe, this would have to collapse to form galaxies between 300,000 years from the Big Bang and, let's say, 400 billion years after the Big Bang. This is too short amount of time to grow those density perturbations enough to form galaxies. But if we have dark matter, then clumps of dark matter can be formed earlier, before the recombination, before the cosmic microwave background was emitted. And so the matter could start to condensate in these seeds that grew to form galaxies were starting to condense earlier on in the history of the universe. So without dark matter, it would be also difficult to form galaxies in such a short amount of time. And in addition, it would be difficult to have spiral galaxies, because this could not be stable if we didn't have dark matter.
And then another question is, so we will find the elliptical galaxy only in a dense version, as you mentioned. Is that right?
Yes, this is an observation. This is the plot. You can see this is the fraction on the y-axis. You have the fraction of population of elliptical, lenticulars, and spirals and irregulars. And on the x-axis, you have the density compared to the average density of galaxies in the universe. And so you see that in the underdense regions, the fraction of ellipticals is order 0.1, so less than 10% of all galaxies outside dense regions is of the order of 10%. Okay. While on the other hand, in underdense regions, 80% of galaxies are spirals. So this is an observational result, which can be explained in the framework that I told you about. But these are observations.
Okay, I don't know if we do have other questions from the participant here. So if you don't have other question, I would like to thank Dr. Nicola Menci again for the nice presentation today about the galaxy formation. Thank you for the nice talk.
Okay, you're welcome. Thank you.
Yeah, thank you for your time and your presentation, and we hope to see you again in another presentation.
Okay, we'll be happy to do it. Okay.
Thank you, everyone. Bye-bye. Thank you.
Bye-bye.
Bye-bye.
Bye-bye.